In this video, we'll be looking over Lewis dot structures and the correct way to draw them. The first step when wanting to draw Lewis dot structures is to find out how many valence electrons the atoms you're going to be working with have. If we take a look at the periodic table, group 1A will have 1 valence electron, group 2A will have 2. We skip the transition metals. We go to column 13, which is called group 3A, and it has 3 valence electrons. Group 4A has 4. Group 5A has 5. Group 6A has 6. Group 7A, the halogens, has 7. And then group 8A, the noble gases, have 8. So once we figure out how many valence electrons our atom has, or the atoms we're going to be drawing have, we can just simply write their abbreviation and then those valence electrons. So if we begin with an example such as sodium, sodium has an atomic number of 11, so it has 11 electrons, but it has 1 valence electron. And we know this because sodium, Na, is in group 1A. So we would draw that 1 valence electron right here, just by itself. Another example would be carbon. Carbon is in group 4A, right here. It will have 4 valence electrons. So we put the first one right here. And the second one doesn't go right next to it. We actually take it to the different coordination spot, so we would put it right here, then right here, and then right here. And then another example we can take a look at would be oxygen. So oxygen is in group 6A. It will have 6 valence electrons. So begin right here. There's 1, 2, 3, 4, and we still have 2 more valence electrons to distribute. So we would come back to our first spot, 5 and 6. So this would be the Lewis dot structure for oxygen. One more example, let's do fluorine. So fluorine, we begin right here. 1, 2, 3, 4. Fluorine has 7 valence electrons, so then 5, 6, 7. It'll have 1 left over before it gets to that full shell. An example such as neon would just be the exact same thing as fluorine, except for 1 more electron right there. So now let's go and take a look at how it would look when we're drawing different molecules. So I wrote all of these different molecules, and we'll go through and do the Lewis dot structures for each one. So let's start off with H2, hydrogen gas. So first you would draw the Lewis dot structure for each one. And we know that hydrogen will look like this. And the other hydrogen, we can put the electron right here. It'll look like this. And when they bond together, these two would come together to make a bond. And when it's a single bond, it's known as a sigma bond. So this is a single bond. Also known as a sigma bond. And it looks like this. That's the symbol for a sigma bond. All right, so our next example is H2O, water. So we would draw this, and then we would put hydrogen right there. And to know which atom would go in the middle, we want the least electronegative atom in the middle, except if it's hydrogen, because hydrogen can only bond to one other thing. So we wouldn't want hydrogen in the middle, so our only option is oxygen. So then we would put oxygen right here, and then the other hydrogen. And oxygen has 6 valence electrons, so 1, 2, 3, 4, 5, 6. And then hydrogen has that 1, and we'll put that right here. Now, this electron would come over and bond with this one. So these two would bond. And then this one and this one would bond. So our final result would look something like this. So there's a single bond right there, and then oxygen, and then a single bond right here to hydrogen. And then we had these two electrons right there, and these two electrons left over. So then these two would be our lone pairs. So the Lewis dot diagram for oxygen would look something like this. Going on to HF, again, hydrogen's right there. Fluorine, will draw it in a way where the lone electron will be right here. So we'll start off right here. And notice how this one's left over. So 1, 2, 3, 4, 5, 6, 7. And then hydrogen has one valence electron. And these two come together to form a sigma bond. Again, with the molecules that have multiple bonds, you want the least electronegative atom, except for hydrogen, to be in the middle. So with carbon, carbon will be right here. And it'll have those 4 valence electrons. Then each hydrogen will attach to the side. And then our result will be methane, which is like this. So 4 sigma bonds. All right, let's go over to NH3. So again, least electronegative atom in the middle. We can't use hydrogen, so we'll go with nitrogen. Oh, that's the final step. Let's go back. So we have 1 right here, 2, 3, 4, 5. And then we have 3 hydrogens. So let's draw them right by the lone electrons. So we'll have our hydrogen with 1 electron, hydrogen with 1 electron, and hydrogen with 1 electron. So then this lone pair will be by itself. The overall result, if we turn it this way, so we'll turn it 90 degrees this way, we'll have nitrogen with a hydrogen here, a hydrogen here, a hydrogen here, and those 2 lone pairs. Notice we just turn this. It's the exact same thing as we have up here. So 3 sigma bonds and then a lone pair. And then let's go to CO2. Now CO2 is an interesting example, and we'll see why right here. So we'll have the carbon and then the 2 oxygens. Out of these two, the carbon is the least electronegative atom, so it'll be in the middle. And then it'll have 4 right here. And then we'll have oxygen. So oxygen will be right here. And we'll have 1, 2, 3, 4, 5, 6. And then another oxygen. 1, 2, 3, 4. I'll draw it right here. So 5, 6. So these 2 are lone pairs. And then what we see is that these 2 will form a bond, and these 2 will form a bond, but then we're left with 1 lone electron right there, 1 lone electron right there, 1 lone electron right there, and 1 lone electron right there. When this happens, there can be an additional bond, and this would be called a double bond or a pi bond, and that occurs when the lone electron of one atom bonds to the lone electron of another atom after there's already been a sigma bond. So these 2 would bond, and then these 2 would bond, and our overall result would be a carbon with a double bond to an oxygen right there, and a double bond to another oxygen right here. And then notice we have the 2 lone pairs right here. So 1, 2, and then 1, 2. That was this one and this one. And then notice the other oxygen has 2 as well. So 1, 2, 1, 2. And then the carbon doesn't have any more lone electrons, so we're all set. All right, so this example I'll draw down here. So again, nitrogen has 5 valence electrons. And then we'll do the other one right here. One, 2, 3, 4, and then we're going back around. So just for simplicity, I'm going to draw the 5th one right here. So these 3 are facing these 3. All right, so what we would have is these 2 would form a sigma bond, but then we see that there's a lone electron, a lone electron, a lone electron, and a lone electron. This one can potentially bind with this one, and this one can potentially bind with this one. So our overall result for N2, nitrogen gas, would be a nitrogen with 1, 2, 3 bonds bonded to another nitrogen, and then we have these lone pairs. These go right here. And then these lone pairs would go right here. And then that would be the Lewis dot structure for N2. And then in all of these, the very first bond was a sigma bond, and the second one, so our first example of a pi bond was right here. This is going to be a pi bond. So pi, like that. That's the symbol for a pi bond. And then if you have a third bond, as we do right here, a triple bond, the very first one, that one is a sigma bond. And then this outer one right here, and this outer one right here, are going to be pi bonds. So 1 sigma bond and 2 pi bonds in the last one. And what we see is that in all of these cases, when we drew the Lewis dot diagram, the atoms all had a full octet. So hydrogen, if we go back to our periodic table, hydrogen has 1 valence electron. It needs 1 more to be stable. So by bonding right here, by bonding to another hydrogen atom, it pretty much shared this electron through a covalent bond. It shared it, so it feels as though it's full. It feels as though it's in that stable state. In the case of oxygen right here, it had 6 valence electrons, and then it bonded to 1 hydrogen here, and it's sharing this electron right there, and it's sharing this electron right here. So 6 plus 2, 1 for each hydrogen that it's sharing with. It feels as though it has 8 electrons, and therefore it feels stable. It's in its stable state. In the case of HF, hydrogen just needed to gain 1 to be stable. It did so right there. Fluorine needed to gain 1 more as well, and it did so. So fluorine feels full and stable. Hydrogen feels full and stable as well. Same thing with methane. The carbon needed to gain 4 to be stable, and it did so by bonding to 4 hydrogens. The hydrogens each needed to share 1 electron to feel stable. In the case of nitrogen, the nitrogen had 5 valence electrons. It needed 3 more electrons, and it got so with these 3 hydrogens. So 1 right there, 1 right there, and 1 right here. In the case of CO2, this carbon needed 4 electrons, and it got that. So as we can see right here, this carbon had 4 valence electrons, and then it's sharing this electron, or these electrons, with the oxygen. So 1 from here, 1 from here, 1 from here, 1 from here, to add 4 more to the 4 valence electrons that carbon already had. And in the last example, nitrogen, it had 5 valence electrons, and it needed 3 more bonds, and it did so right here. So the nitrogen has its own, so 1, 2, and then it's half of each of these bonds, so 1, 2, 3, 4, 5, and then it also is feeling as though it's full and stable by sharing these other electrons with this nitrogen right here. So 1, 2, 3, 4, 5, 6, 7, 8. It feels as though it has a full shell.